Welcome students. I am Dr. Monika Khetarpal, Associate Professor of Physics in Government Dungar College, Bikaner. In my lecture series of MSc Final Physics, we were discussing superconductivity. We have discussed various theories which were used to model superconductivity. The most important theories were VCS theory, Landau equation. Now, in today's lecture, we will discuss Ginzburg-Landau theory. This theory is a mathematical theory which is used to model superconductivity. This theory is based on a complex order parameter psi. This complex order parameter, it has a value non-zero only for temperature less than Tc. That means when the material is in superconducting state. This complex order parameter psi, it vanishes when temperature is above Tc. That means when the material becomes normal. So we will define superconducting state in terms of a new parameter which is termed as order parameter, and its validity is only for the temperature range T less than Tc. That means in the superconducting region. This psi has some properties. First property being that it approaches to 0 as T equal Tc. That means it has a value 0 when material becomes normal. And its modulus square gives us the density of superconducting electrons. Psi modulus square is equal to ns. As similar to the wave function of a Schrodinger equation. Psi r square give us the probability, whereas in this case, psi r square, it determines the density of superconducting electrons. So using this psi complex order parameter, scientists Landau and Ginzburg, they assumed that free energy of a superconductor, this is the free energy of a superconductor, Fs, it can be expressed in terms of this complex order parameter psi as Fn plus alpha psi square plus beta upon 2 psi raised to power 4 plus minus iota h cross delta minus qa, this whole square upon 2m plus mod of b square upon 2 mu 0. Here we have assumed that we are neglecting the higher order terms of psi as well as smallest of its gradient is assumed. Now, this expression contains various terms. What are these terms? Starting from the first term, Fn, n denotes normal state. That means this is the free energy in the normal phase. These alpha and beta, alpha in second term, beta in third term, these are phenomenological parameters. In this term, we have Q. What is Q? This Q equal to E. Because in superconductivity, we always deal with two electrons, which form a Cooper pair. E is the charge of a single electron. So, in spite of Q, we have 2E. A is termed as electromagnetic vector potential. And the other parameters, the last term, B, includes B. B is the magnetic field strength, and B we know that is related to A by expression B equal to curl of A. Mu0 is magnetic permeability in vacuum. Here in this expression of free energy of superconducting state, we have various terms, and this term denotes the kinetic energy. We know that kinetic energy equal to P square upon 2m. This is the kinetic energy in the presence of magnetic field. And the last term, B square upon 2 mu0. This term is the magnetic field term. So now we will derive our two Ginzburg-London equation using this expression of free energy of superconducting state. What does Ginzburg and Landau do? They minimize the free energy with respect to order parameter in order to obtain the first GL equation. Minimize means I have to differentiate Fs with respect to psi. That means del Fs upon del psi. This must be equal to 0. So I am differentiating this. This term does not contain psi, so its differential will be 0. Differential of second term will be 2 alpha psi. Third term 4 beta psi square psi upon 2 plus differential of psi. Differential of this psi, this whole term is constant, square 2 psi. This term does not contain psi, so its differential will be 0. Now simplifying this expression, I got my first GL equation, Ginzburg-Landau equation. This first GL equation, it is similar to time-independent Schrodinger equation. What is the time-independent Schrodinger equation? Time-independent Schrodinger equation is minus h cross square upon 2m del 2 psi upon del x square plus ux psi x is equal to E psi. But here we have, this is as we have already stated, kinetic term. The difference between the time-independent Schrodinger equation and the first GL equation is that in this GL expression, there are non-linear terms also. Now, as we have derived first GL equation by minimizing the free energy with respect to order parameter psi. Now we will derive our second GL expression. For this purpose, what we will do, we will minimize free energy with respect to vector potential A. What does it mean, minimizing free energy with respect to vector potential? It means that derivative of free energy, that means Fs with A, it must be equal to 0. So differentiating our free energy, this free energy with respect to A, we get the expression of current density J equal to 2E upon m psi star minus iota h cross del minus 2E, because charge Q equal to 2E, vector potential A psi. This is second Ginzburg-Landau equation. This second Ginzburg-Landau equation, this provides the superconducting current. So from the Ginzburg-Landau theory, we have derived two important expressions. The first Ginzburg-Landau equation is in terms of order parameter, and it is similar to the time-independent Schrodinger equation with the principal difference that there are non-linear terms. And the second equation, which is obtained from free energy by minimizing with respect to vector potential A, we obtain electrical current density J. So this is an important theory. It is a mathematical theory which is used to formulate superconductivity. Thank you, students, for watching.